This video is part of CAE Associates ANSYS e-learning series. CAE Associates is an engineering consulting firm in Middlebury, Connecticut, specializing in finite element analysis and computational fluid dynamics. We have been an ANSYS channel partner since 1985 and have developed our ANSYS e-learning series to help you maximize your software investment. Please visit our website, which includes an extensive resource library with over 250 items and counting in an easily searchable area. We also invite you to visit our Engineering Advantage blog, where we share insights from our many years of performing engineering analysis. CAE Associates also offers an extensive schedule of ANSYS courses taught at our Middlebury office. If you need help deciding on the best courses to take for your application, visit our CAE University page. The complete library of e-learning recordings is available for viewing in our resource library and also on our YouTube channel at youtube.com/CAEAI.
Okay, good afternoon, everyone. This is Pat Cunningham from CAE Associates. I'd like to welcome you to our lunch session of the Submodeling e-learning seminar. We're talking about using version 14.5 today because in the 14.5 release, there have been several tools added which make submodeling much more feasible for us in the workbench environment. Today we're going to be talking about submodeling. Submodeling is something that has been available to us as a tool in the mechanical APDL environment for quite some time. It's based on St. Venant's principle that if you have two different load distributions that are statically equivalent, effects on a location a sufficient distance away from the load application area should be the same. And so for our standpoints here, what we're talking about is a load distribution based on two different meshes. And if the area of interest between our two different meshes is far enough away from that region, we can be confident that we're going to be getting the same result. So how we apply this in the finite element world is that we create a fairly coarse model of an entire system, and then if we want to go and look at a very discrete region without having to resolve the entire model, what we'll do is extract a submodel region or an area in the middle of that model. We'll take the global displacement solution from the original model based on St. Venant's principle. We'll apply that to the cut boundaries of our submodel. And that's really what we'll be talking about today. It gives us the advantage of not having to regenerate the entire finite element solution if we're just interested in looking at a detailed response in a particular or specified area. So some basic characteristics of submodeling, if you're not familiar with it. The submodel is a separate analysis or a separate model from the global model. The submodel typically only includes the local area of interest. So you're going to go to your global result, take a look at a particular region for stress, say, okay, I'd like to get some more resolution in that region, slice a piece of the model out from that area. It has to be geometrically in the same location because we're going to be interpolating displacements based on nodal coordinates. We're going to remesh that geometry with a finer mesh. We'll interpolate those global displacements onto the finer mesh, and then we'll generate our submodel solution. And that's really what we'll be doing today in the presentation. As I mentioned a moment ago, submodeling has been available in mechanical APDL, or what we refer to as the ANSYS Classic interface, for a long, long time. Submodeling was possible in Workbench, but prior to the release of version 14.5, required APDL command blocks to accomplish the cut boundary interpolation. There were two solution phases that were involved where you had to write out files and then read files back in. It worked reasonably well. It followed the same basic procedure that we use in mechanical APDL, but it was a little bit cumbersome. One of the nice things about version 14.5 is that they've reduced that entire effort to simple drag and drop operations. We can have our global model and our submodel inside the same project. That's highly advantageous because we can simply make a duplicate of our global model and then edit that geometry locally to extract the submodel region. Then when we're ready to interpolate those boundary conditions, we grab the solution row from the global model, drag it, drop it onto the setup row of the submodel. And that's what we'll be doing today. The basic procedure for submodeling in the Workbench environment consists of the following steps. We're going to set up and run our global model the way we normally would. We're going to either bring in separate geometry or make a copy of our global model and extract the geometry that we want. The main requirement here is that that geometry has to be in the same geometric location as it was in the global model. We're going to then drag and drop and interpolate the global displacement fields onto the cut boundaries of our submodel. We're then going to evaluate the submodel boundary locations, and that's something you have to be fairly sensitive to when you're doing submodeling. You want to make sure that you are, as we mentioned earlier on in the presentation, far enough away from the region of interest such that that cut boundary interpolation of those displacements isn't affecting the localized response. So we're going to talk about two different ways to compare, in this case, force and then stress at those cut boundary locations to the global model. There's some nice new tools in version 14.5 which allow you to evaluate that fairly readily. Then once you're confident that your cut boundaries are in an appropriate location, you can simply go in and evaluate the submodel results the way you normally would with another model. So just as an example, the types of things that we typically use submodeling for, typically in a global model, we're reducing that geometry to its simplest form. We're trying to take out a lot of features, fillets and chamfers and rounds, things that are going to require more elements in the global model at a point where we're not necessarily interested in getting a refined stress. So in my global model in the upper left, you can see here that we have a fairly coarse brick mesh, and we have a reentrant corner or a sharp edge in the region where we're looking at a high stress in that global result. Now we know based on experience that we can't evaluate the stress accurately in the global model in its current geometric condition because at a reentrant corner that stress is going to be infinite. So what we need to do is go back and fill in that region with some geometry, like a fillet radius, something that would, a tooling radius, something that would actually occur in the real part. The reality of the situation is we can't make a part or manufacture anything that has a reentrant corner in it. It's got to have some small fillet radius. We need to go back and put that in to evaluate the stress accurately. So on the lower right-hand corner, we're showing our submodel stress distribution. And in this case, we've even switched element types. So we go in, we add the fillet, we remesh it in a much finer state with even a tetrahedral element based compared to the original brick element, and we're able to interpolate or share those global boundary conditions to very quickly evaluate the submodel. So I'm going to switch over now to the ANSYS mechanical environment, and let me just bring up my global model here, just give you a quick idea of what we're doing. So we have, some of you have seen this before if you've attended our update seminars. We have an assembly of essentially a grip or a plier, and we've applied some load to this such that we end up with this high stress right at that reentrant corner where we're missing that fillet. So my options for evaluating this type of situation are two, basically. I can refine the geometry in the global model and regenerate the entire global solution. Not really a big deal with this model because it's not terribly large. But if I had a very big, complex assembly, I may not want to do that. I may want to run that global analysis one time and then utilize those cut boundaries to evaluate the stress and maybe even do a mesh refinement study on a local level using the submodel. So that's what we're going to do today. We return back to our project page now. Up on the top here, I have my global model solution. And in order for me to easily create this submodel, I'm simply going to go to the geometry row, right-click, and duplicate that system from the geometry level. Now, when I duplicate at the geometry level, this new system comes up, and it has an independent geometry associated with it. So in this case, I've loaded in a SolidWorks part, as you can see by the little red cube icon to the left of geometry. I could go back to SolidWorks, and I could extract my solid model geometry there if I chose to. But for me, in the Workbench environment, Design Modeler is far much more convenient to do that. So I can right-click here and now edit this submodel geometry locally in Design Modeler. When I do this, because there are no links here, I'm not affecting the global solution at all. It's a copy of that global solution. So we open that up in Design Modeler. I like to use Design Modeler for this because I find it's very well suited for cut boundary extraction. I can simply use planes or I can use surfaces. I can use whatever I want to basically cut out the region of interest. So in this case, I've placed 3 planes, and I've used some slicing operations to cut out just the area of my submodel. Well, I mentioned a little earlier that it's very important that your submodel cut locations are far enough away from the local area of interest. And you may not necessarily know what that is up front. The nice thing about using Design Modeler in this case is each one of these planes can be parametrically defined. So I can evaluate my initial submodel. I can determine whether or not those cut boundaries are far enough away. If they're not, just simply parametrically modify that model by changing the offset value that I'm using for my plane and hit the update button or the refresh button to just recreate the submodel solution. So essentially with the setting one parameter value and one button at the top of the screen, I can very easily just refresh my, my submodel solution and gain confidence that my boundaries are in the right location or in adequate locations. Now, additionally, we may want to add some of that geometry in. So if that was a feature that you had suppressed on the CAD side, you could simply unsuppress it. I'm doing the same sort of thing here. I'm just going to add in a fillet radius in that local region so that we can evaluate that stress. Again, this fillet radius doesn't have to exist in the global model. That's the whole advantage here of evaluating the stress on a submodel basis. So we return back to our project page. We have our submodel cut out, and then to get the connection between the global model and the submodel intact, we simply grab the solution bar, drag it, drop it onto the setup row of the submodel. When we do that, we take a look at the submodel here. We'll see that we have a submodeling folder located in the structural static solution. That came from the fact that we dragged and dropped the solution from the global model. Now, one thing that I want to point out before we go any further here is I mentioned comparing forces at those cut boundaries between the global and the submodel solution. ANSYS, by default, does not save nodal forces in the solution. You can go to your Tools Options menu, and you can tell it to do that by default. Strongly recommend that you do that. Otherwise, you have to make sure that you go to the analysis settings and turn on that nodal force solution for every particular analysis that you're going to do. If you don't do this and you try to look at the forces on that surface, that cut boundary surface, it's going to tell you that that data is not available. You're just going to simply have to rerun the analysis and duplicate what you just did. So very important. Again, I strongly suggest you turn on the nodal forces as a default. You'll find that up in the Tools Options menu for the mechanical environment. So we're ready now to start interpolating those boundary conditions. We go to our submodeling folder, right-click, and we can choose to insert either a body temperature or a displacement. Body temperatures would come from a global thermal analysis where we needed to get the thermal load onto the body. In our case, we're going to be interpolating or bringing across displacements on those cut boundaries. I've already done that for a couple. It's very important as well, in addition to saving those nodal forces in the solution, that you apply the cut boundaries on the individual cut boundary surfaces as individual displacement imports. The reason for that is we're going to look at the total force, or the F-sum, for that particular displacement load. So we don't want it all summed together from the different cut boundaries. We'd like to see it individually on each one. So I've gone through and I've imported each one of these cut boundary solutions or cut boundary displacement fields onto my finer mesh from the global model. Now you can check the validity of that interpolation. There's a couple of mapping controls that you can use. You can change from program control to mapping, and you can set some of the different options for bringing in that mapping if you find that it's not mapping those loads the way that you had intended. So we put our cut boundary displacements on. We also have to make certain that any other boundary conditions that existed in this region of the global model are also applied to the submodel. In my case, the only one was a frictionless support that I had on the backside because I had made a copy of the original global geometry and extracted the submodel from it. That frictionless support is added for me automatically because that face tag is the same. If you were using a separate model from the CAD system, you want to make sure that you go through each one of the boundary conditions. You may have pressures applied. You may have, as we saw, temperatures or body forces applied. You want to make sure that anything that existed in the global model also exists in that same location of the submodel. We generate our submodel solution. We can take a very quick cursory look at the displacements and compare it to the global model for that region. But of more use to us is to determine whether the force response at the cut boundaries matches between the global and the submodel. We do that by inserting a reaction probe. So it's just simply a right-click, insert a probe in this case for force reaction, and then you'll see the various displacement loads that you can choose from. So we've already done that here, and we can see we have a total force. We get a force vector on the front of this cut boundary number 1. And we have a total force of about 108.45 pounds. Well, let's go back now and compare that to the global model. Shrink my submodel down a little bit. Move it over to the side here. Let's bring our global model back for comparison. Okay, well, now we have, actually, let me get a little bit bigger here. Now we have a little bit of a dilemma here, because you'll notice that there's no mesh boundary in my global model that matches the submodel. The cut boundaries in this case don't exist in the global model. Sometimes you can set it up such that that's what you want to have happen, but you know, in most cases we don't really know where those cut boundaries are going to be. So what we need to do is find a way to interpolate the forces onto the location where we place the cut boundary. Well, we can do that at 14.5 using construction geometry. Construction geometry is usually found up on the toolbar. When you add it to the outline tree, you'll have access to it, and you can right-click and insert a path or a surface. In this case, we're going to be inserting a surface, and we're going to align that surface with a particular coordinate system. I've created a coordinate system here called cut boundary number 1. It's at that same location as the cut boundary in the submodel, and I simply align the surface with that particular point. So now I've got a surface in place. Now I can interpolate stresses and forces onto that surface. And the force interpolation is something that's new at 14.5 that makes it very easy for us to check and compare these boundaries. So we get at that by, once again, right-click, insert a probe for force reaction. Again, you want to make sure that you've saved those nodal forces during the solution, otherwise you have to regenerate the global solution as well. In this case, in the place of a boundary condition scoping, what we're going to do is scroll down to the bottom and you'll find that they now have the surface option available to you at 14.5. We specify the surface that we want to use. In this case, we use surface 2, and that's right at my cut boundary. And then we tell it what geometry we want the forces from. We're going to pull the forces from this body. And since we're doing a force summation through the mesh, we're going to tell it, well, those forces are either coming from the positive side or the negative side with respect to the normal direction of that plane. So we'll just leave it on the positive side. They're equal and opposite in this case. If we right-click and evaluate that, we can take a look at that force response. Drag it over here so we can compare now. And in our global model, you can see you get a nice a pictorial distribution of the forces along that edge for that face. You get the total vector. In this case, it's equal and opposite to what I was showing on the submodel because of the side that I picked. But when we look at the total force, or the SRSS of those forces, we can see that the maximum value is 108.21, which is pretty close to 108.45. So I think we're within some computational error there. We don't need to worry too much about moving that cut boundary. So that's the best way to check and make sure your forces are summing or adding up correctly on both the submodel and the global model. We can also compare stresses on those locations. So let's go back here. Actually, I don't have I invalidated my solution, so I don't have a stress response. But what we could do is also scope a stress to that surface, and then we want to just go back and compare it to see that the stresses are similar in both magnitude and distribution. So I'm just going to pop my PowerPoint document back up here. Moment. Scroll down to the bottom here. So looking at this solution here, you want to verify that the stresses look similar. Again, depending on the mesh that you use in the submodel, that distribution may vary a little bit, but you want to see that the magnitudes are roughly the same based on that force distribution. And again, we're using a hexahedral versus a tetrahedral mesh, so I may want to refine the mesh a little bit further on my submodel here, and I'll get a more matched response with that global model. So that's basically the procedure that you use. The important items to keep in mind are A, make sure you've saved those nodal forces during both the global and the submodel solution. If you can put the cut boundary planes in one geometry model, if you're using Design Modeler, place them up at the very top in the beginning of the process, and then you can very simply grab those, make sure you import those into the global model on the mechanical side, and you can use those to do the surface interpolation. Otherwise, you always have the option to just recreate a coordinate system in mechanical to evaluate what's happening on those cut boundaries. One more thing I just wanted to show you here. When we're back to that submodel stress, once we're happy with that submodel stress, we may want to go in now, or happy with the cut boundary location, we may want to go in now and automate a mesh refinement study to make sure that we have a sufficient number of elements in the submodel to capture the response that we're interested in. Once again, we can take advantage of the parametric nature of the workbench environment. I've specified that my face sizing that I applied in that global fillet region is parametric, and I went over to the design point table and specified a couple of different mesh sizes, and then kicked off an automatic run where it just loops through, changes that element size, redistributes those cut boundary displacements, and generates the submodel solution. And you can see as I decrease the element size in that region, my stress is eventually leveling off to a point where it's not sensitive to the size element that I'm using in that area. And again, in the past, we would have to do this manually by changing, checking. Now I can just set up a table, kick off a couple of runs, and evaluate for myself if I have a sufficient number of elements in that region. Okay, so I'm going to return now to the WebEx window here, and we're going to invite you to offer questions. If you'd like to use the chat window, you can type in your questions there.